All right, let me make a video solution here for number 10. So chapter, let me go blue here, sorry. Chapter, what is this, 24, number 10. Gotten a few questions. It's one that really hits to the heart of this chapter. Visualize this for a moment. It says here, a particle of charge 12 microcoulombs is placed at the center of a spherical shell. All right, so I'll make a little charge, if you will, there. There's the 12 microcoulombs. And then surrounding it, I'll do in red, because I'm going to call that a Gaussian surface in a minute. But there's my sphere around it. And the electric field would look something like this, and so it would be pointing outward, and so we know that the flux then would be positive. And that's the question A. What is the total electrical flux through the shell? So this was the definition of electric flux, E dot dA. But the real key to this problem is Gauss's law, which says if you do it on a closed surface. Okay, so this sphere is a closed surface. So even though this is the general definition of the flux, we're doing it along a closed surface. And it says if you do this integral along a closed surface, you will get the charge that is inside of that Gaussian surface over epsilon naught. So the point of this problem really is to realize that. Don't actually do this integral. That integral is the flux. You can do this side really easy. This just becomes then the charge, which is the 12 microcoulombs that is inside, divided by the epsilon naught, which is the 8.85 times 10 to the negative 12. So, grabbing my calculator, I've got my 12 and make it a micro times 10 to the minus 6, and then divide that by 8.85 times 10 to the negative 12. I get, how many zeros are there? 1, 2, 3, 4, 5, 6. So this comes out to be 1.36, and it's 1, 2, 3, 4, 5, 6. So it's mega. And then the units here, maybe I should write them out. I put in that as a micro, so that's a coulomb in the top. But down here, the units for this are Newton meters squared, coulomb squared. So that the coulomb in the top cancels with 1 there. And if you flip it, then you get Newton meters squared over coulombs, which is perfect units, because this is the units for the electric field, and this is the unit of area, so that would be the unit of flux. An electric field, times an area. So that's A, and that's how it's supposed to be. And they didn't really want you to do a whole integral. Visualize this. And this is kind of a training exercise into visualizing it. Because then B says pick any hemisphere of the shell. Okay, now any hemisphere, I'll just do how about a bottom hemisphere? And so maybe maybe I'll just redraw over here. So here's the 12. Here would be this cross section, and maybe try to make it 3 dimensions. I'll put an equator. But we're talking about this bottom half here. And hopefully, again, visually, you can see that all of the flux goes through a sphere, and that means half of it would go down in the bottom half. Or if you did a left hemisphere, then half of it would go that way. If you did a right hemisphere, half of it would go that way. You did a top hemisphere. But the bottom line, it's 1/2. So it's 1/2 of 1.63 mega Newton per coulomb meter squared. And so if you take half of that, so come back over to the calculator, divide by 2, 1, 2, 3, this is 0.678 mega Newton coulombs meter squared. Although I think the solutions then move this 3 decimals, so it's 678 and kilonewton coulombs meters squared. So that's the main part of this then. And the last part, C, well, let me go back to the question, see what it says. C says, do the results depend upon the radius? Now, again, I suppose if you did the math, you would see that in this equation right there, there has a 1 over r squared, the radius of the equation for the electric field from a point, and then here in the area, you would have that 4 pi r squared, and if you went through the math, the r's would cancel off. But again, that's not really how they want you to do it. They just want you to come back to this picture here. And so if you come back to the picture and you draw a smaller sphere, you get the same number of lines going through there. You draw a bigger one, you get the same number of lines to go through. So the simple answer is no, it does not. And explain, well, like I said, you could do it either way. You can do it this way mathematically, saying the field gets weaker the further you away, but the area gets bigger by that same proportion. So the product of the two remains the same. So there would be the math answer. And then the visual physical picture answer, which I probably think is more important here moving forward into the chapter, is that it's the same number of lines. No matter how you draw them, the lines just extend out. And of course, that's our whole point. They would be further apart on a big radius than a small radius. And that's how we measure the strength of the field, by the concentration of them. So a radius here would have a strong field, but a small area, and something out here would have a weak field, but a big area. So again, simply no.